All right, we're going to talk about something that we actually talked about a little earlier in the year, maybe even in this chapter. Yeah. Okay, yeah, it was that chapter when we talked about the sum of the angles. What is the sum of the angles of all three angles of a triangle? 180 degrees, okay? So we actually talked about that. We mentioned it. I don't know if you remember me saying this, but a lot of times I'll say this. I'll say, okay, what I'm teaching now, it's free of charge. I'm not going to charge you for it. You know, you remember me saying that? Okay. I mean, it's just kind of a silly little thing, but um, I said you're going to learn that a little bit later. Well, guess what time it is? It's later, right? So that's what we're going to learn right now. Let's take a look. Come on, pay attention. Leave the silly comments to me, all right? All right, so what kind of triangle do I have right here?
Obtuse.
Isosceles. Yeah, it is obtuse, but as far as the sides go, it's almost said it. It's isosceles. Do you remember how to spell isosceles? I-S-O-S. Celine Dion, right? C-E-L-E-S. Okay.
With two E's.
No, that's a C. It just looks like a curly little deal there. If that bothers you so much. Is that better? Okay. Isosceles. So it's an isosceles triangle. Now, we alluded to this before, but now we actually have a theorem. And we're not going to prove the theorem. It's actually proven in the book if you want to. It's proven on page 284. It's right in the middle. It says proof. Okay? I'm not going to do that in class, but you can look at it if you really want to. So it is a theorem, so that you can prove it. But let me just tell you what it says. Actually, you know what? Before we do that, I know you're excited about hear this theorem, but we got to label a couple things here. If I have an isosceles triangle, do you see this angle that's opposite this equal side?
Yes.
And this angle is opposite this equal side. Agree? Well, we haven't said that yet. Anything about that. I'm just naming them. This is just vocab right now. Then I'll tell you something about the angles. Okay, we call these the base angles. Base angles.
Because they're at the bottom?
Well, they're across from the equal sides. Okay, so we call those the base angles.
So even if you flip it upside down, those.
Yep, it doesn't matter how it's twisted or anything. It doesn't have to be on the bottom necessarily, but as long as they're opposite the equal angles, then they're base angles. Make sense?
Mm-hmm.
Okay, this angle that's not the base angles, we call that the vertex angle. I probably won't refer to this all that often, but it's there. It might be nice to know. All right? Let's talk about the two sides. The two sides that are equal to each other, we call the legs of the isosceles triangle. That's a leg, and that's a leg. All right? I guess I should just put leg instead of legs for that one. That's just one leg, right? Mm-hmm. All right, and this thing, now if these are base angles, what do you think this side is called?
Base.
The base, very good. Okay, so it's the base. Notice that the base angles connect one of those equal sides to the base. You got it? All right, so they're base angles. That's just a little vocab. That's all you need to know about that. You okay with that? All right. I'll keep all that writing in there. Let's just change to a different color here. Now let's talk about the actual value of these angles, the measurement of these angles. So here's what the theorem says, and there's a proof for it. I'm not going to prove it for you right now, but there is a proof for it. But what it says is this: if I have two equal sides, or an isosceles triangle, if I have two equal sides on a triangle, then the opposite angles are going to be equal as well. So I got two equal sides, right? The angles opposite those equal sides are going to be equal. Does that make any sense what I just said? Got two equal sides. The angles opposite those, which would be called the what? The base angle. So basically, we could shorten it, just say the base angles are equal on an isosceles triangle, couldn't we? I don't think they say that exactly in the book, but that would be a nice little way to say it. Let me say it again so you know what I'm saying. The base angles of an isosceles triangle are what? Are congruent or equal. Exactly. You got it? Make sense? All right, so if I have a triangle with two equal sides, the opposite angles are equal. We have that. We give that a name, and that's called the isosceles triangle theorem. So isosceles, I'll write it down again. Isosceles, I'll just shorten that, triangle theorem. So basically what it says is this. Watch. I'm going to write it as an if-then statement because there's something I'm going to do in a second. Watch. So if the two sides, this is just real shortcut, okay? If two sides are equal on a triangle, then, I always like to write if-then statements. So if two sides are equal, then the what? The opposite, what?
Interior.
No, I never said anything about interior. They're all interior angles. The opposite angles are equal, right? I'm just trying to shorten it up a little bit. That's basically, in a nutshell, what the isosceles triangle theorem tells us. Make sense? So if two sides of a triangle are equal, then the opposite angles are equal. Well, what if I switched it around? What if I switched the if and the then? Do you remember what we call that? We have a special name for that. It's not inverse. It's close. It's converse. Okay? It's converse. Now, there is a thing called the inverse, and that's kind of in Chapter 2. Remember we skipped Chapter 2? But we're going to talk about converse right now. So the converse of the isosceles, I'll just shorten it, isosceles triangle theorem, okay, says this. What's the converse of this?
Then
If the what? No. We start off if, but we switch the if and the then. We don't start off with the word then. We take the stuff with the then and we put it on the if. So if the two opposite what?
Opposite
Angles are equal.
two sides are equal.
That's right. So we can go backwards, can't we? So if these two angles were given to be equal, what do you think I could say about those two legs? They're going to be equal as well. So if the two opposite angles are equal, then the what?
Two sides are equal.
Right, the two sides. Well, so let's say two opposite sides. Is that all right?
Cool with me.
The two opposite sides are equal. I just kind of wrote it down just so you could see. But that's basically what it says. So that's the isosceles triangle theorem. This is the converse of it. Now look, I told my last class, if you want to, if you have to use this as a reason and a proof, I'm fine even if you're using this. If I give you a triangle, let's do this. If I gave you a triangle, and let's just make this look a little bit different. Just a little smaller. I don't know. I really didn't make it different, did I? Just made it smaller. Who cares? We'll just keep it the same size. Sorry. Watch. If I'm given that this angle is equal to this angle, let's call this ABC. If I'm given that that B is equal to C, what can you tell me just from that information? That AB equals what? AC. And you can give me a reason for that. So it's given that the angles were equal. We figured out that AB is equal to AC. What would your reason be for that? Technically be the converse of the isosceles triangle theorem. If you just want to write now, if geometry teachers are listening to me right now, they may be having a fit. But I'll just let you say this. I'll let you just say isosceles triangle theorem. Either way. Okay, so I don't care. If they give you the two sides equal, and that means the two angles are equal, what's the reason? Isosceles triangle theorem. If they give you two angles equal, and that means the sides are equal, you can still just say isosceles triangle theorem. I'm fine with that.
We're allowed to say
It's
the
not that
converse
big.
if we want to.
If you want to, you can. Yeah. In fact, it all depends on the author of the book. I taught out of another book that never called this thing the isosceles triangle theorem. All right. It depends on the author of the book what they want to call things. Basically, what we used to basically do is this. In the other book, I would write this stuff out as a reason. So if I was given these two angles equal and I had to show that these two sides were equal, this would have been my reason. I would have written this whole thing down right here. But this book just shortens it up. They give it a name. That's always kind of nice if they give it a name, don't you think? All right. Does that make any sense?
Yes.
All right. Let's do this. Let's pause this and I'm going to clean it all up. So now what we're going to do, we talked about postulates. What's true about a postulate? It can't be proven. We just accept it as fact. What's true about a theorem? You should be able to prove a theorem, okay? Now, some theorems are harder to prove than others. We personally, as a whole, maybe can't prove every single theorem out there, all right? But they can be proven, though, okay? Theorems are something that should be able to be proven. This next thing is called a corollary. Make sure I spell it right. C-O. Yeah, that's right. O.
Can like a theorem graduate to a postulate?
Well, a theorem can always be proven. So, I mean, like a postulate. When I said, like, when I have two parallel lines cut by a transversal, then the corresponding angles are equal. There's really no way to prove that. We just know it. Right, we just know that one and that. Now, alternate interior angles, though, you can use this stuff. Watch. If I know that the corresponding angles are equal, right, and then this and this are equal because of what reason? Vertical angles, right, this one and this one, then what must be true? Here and here. So we have to start with some basic fact and knowledge. Our basic fact and knowledge is that corresponding angles are equal. I would never be able to say that alternate interior angles were equal unless I already knew that the corresponding angles were equal. Does that make any sense? So, I don't know. I don't want to go off on that too much. That's too much already. So what these things are is corollaries. It's kind of like a corollary is kind of like a baby theorem, all right? It's kind of like the theorem is the parent, and the corollary is like the little kid, because it's like an offspring of the theorem. The corollary, it's basically a theorem. You can prove it, all right? It's basically a theorem, but they call it a corollary because it has a lot to do with a theorem that's already been established. So let's take a look at, let's see, do I have a, I don't know if I have an equilateral triangle already drawn. I don't know if I can scooch that over or not. Let me see. No, that just makes it like that. Tell you what, I'm going to have to draw one from scratch. Let me pause this and I'll draw one from scratch. Alright, here I've got a triangle, and it's an equilateral triangle. It's given that it's equilateral. Alright? So that side is equal to that side is equal to that side. So let's go through and kind of prove this next thing we're going to say. I haven't even told you what we're going to prove, but let's just kind of go with it. If these two sides are equal, what did we just learn about the Isosceles triangle theorem? If these two sides, let's label this. Let's call this A, B, C. So if AB is equal to AC, tell me something that you know about this triangle from what we just finished learning. B and C are equal. Angle B is equal to angle C. Agreed? Okay. Now you also know that AC and BC are equal to each other, right? So what does that tell you? That angle A is equal to what? Angle B. Okay? Well, because AC equals BC, angle A equals angle B, right? So if this has one arc, guess what A is going to have? It's going to have one arc as well, isn't it? So guess what? If you have an equilateral triangle, watch. If you have an equilateral triangle, that's also going to be what? Equiangular. Okay? Do you see that? Now I left a gap in there because I'm going to write something in there. It's also going to be equiangular triangle. Watch, it goes either way. I'm going to put arrows pointing in both directions. We use this arrow to represent an if-then statement that goes both ways. If this, or if P then Q, and then it also goes the other way, if Q then P. You get it? So if it's equilateral, then it's equiangular. We can go the other way. If it's what? Equiangular, then it's equilateral. Okay, so if all I know is that all three sides are equal, I automatically can say that the three angles are equal to each other. And we kind of proved it right there, didn't we? Right? We proved it by something that we already have established. We already established that if two sides are equal, the opposite angles are going to be equal. So we just did that. We did it twice, basically, didn't we? We said these two sides are equal, so these two angles are equal. Well, these two sides right here are equal, so these two angles are equal. Guess what? I got all three angles equal to each other. That's my theorem.
That's a
okay?
corollary.
That's a corollary. It's a corollary. They don't give it a special name. Basically, they just say if it's equilateral, then it's equiangular. Got it? Or, and then you got another one that says, you can go the other way, says if it's equiangular, then it's equilateral. Got it? This little symbol right here, instead of an if-then statement, a lot of times they'll say if and only if. When you ever see that phrase, if and only if, that means it could go both ways. Right? So you say if P then Q. We listening? Pay attention up here. If P then Q, then you could say if Q then P. If both of those work, if both of those are true, we call that an if and only if statement. That probably was covered in Chapter 2. Remember we skipped Chapter 2? So there's a few little things in there that I said, we would probably hit later on. So that's that. That's what that little arrow represents. Or you could just write if and only if. All right, enough of that. Let's do one more thing about this. If all three angles are equal, let's find the measurement of all three angles. Well, if they're equal to each other, let's call them all angle X. This is kind of like a little proof again, kind of. So what's true about all three sides? If I add up all three sides, what do I get? 3x, right? 3x. And then what do all three angles add up to be? 180. Because we've already discussed that before. So what's each angle going to equal then? 60 degrees. That's right. Do you remember talking about that a while back? Yeah, a while back we said that was true, and we said we'll get to it later officially. This is officially and this is later. Okay, so there you go. So all three of those are 60 degrees. Every single time. It doesn't matter how big or small your equilateral triangle is. Each angle is always going to be 60 degrees. Thanks. Okay, we good with that? All right. I believe that's all I've got for you. There might be an example or two in there that you can cover on your own. You can look at it on your own. Let me put some problems on here for you to work on. All right, there's your lesson right there. Page 287, 288, 9 to 24. 23 and 24 are proofs. All right, so try them. Don't just blow them off. Don't just put given and then nothing else. All right, try them. All right, bye.